you want me to sit? Do you want to sit there? I see you have a copy of your book as well.
Oh, I have one too.
Good evening, ladies and gentlemen. My name is Howard Burton, and welcome to this London Thinks Ideas Roadshow intimate conversation with Roger Penrose. Let me just give you a brief introduction before I then introduce Roger, and let me tell you a little bit about the format for the evening. First, a brief backgrounder as to why we're doing things in the way that we're doing them. Some years ago, I found myself in the curious position of running a physics institute in Canada, and as part of that, we ran quite a few outreach events. And they always struck me as a little bit of a missed opportunity, because very often we would have extremely distinguished speakers who would speak to a packed audience, much like I see in front of me tonight, and they would give these talks, and people would seem quite happy, and they'd go away, and as they went away, they'd often come up to me and they'd say, "That was wonderful. I didn't understand a thing." And I thought, that's strange, because here you have a speaker who's genuinely interested in communicating her ideas to a broader public. You have a public who's clearly engaged and wants to come out and enjoy things, but there's not much in the way of genuine interaction. So that brings me to the goals of this evening's event. As you all know, Roger has written, this is my very own well-thumbed copy, a new book. And I can tell you right now, for those of you who haven't yet had the opportunity to buy this book and read this book, and you all should, by the way, buy this book and read this book. And I don't work for Princeton University Press, but you should definitely all buy this book and read this book. But it's not an easy book to read. And it's not an easy book to read if you're a layperson, and it's not an easy book to read even if you're somebody who has a technical background. And I think that speaks to what we're trying to do here. We're trying to convey some information, and we're trying to get you excited and involved enough so that you buy this book, you read this book, and you fully explore these ideas. But it doesn't come particularly easy. Einstein once said, or at least was once said to have said, so hard to know with Einstein because he's said to have said so many different things, that if you understand something, you should be able to explain it to your grandmother. And this has been, of course, interpreted in all sorts of different ways, ranging from Einstein being misogynistic to Einstein being somebody who had a particularly intelligent grandmother. But what I want to talk about is the fact that understanding something comes at many different levels. So many people are used to the idea that they read a book, they understand it. They read a novel, they understand it, they put it down. The ideas that we're going to talk a little bit about tonight and that are explicitly invoked in great detail, not only in this book, but also in the references, are ideas that one has to think about, one has to wrestle with, one has to mull over, one has to engage with. And Roger's one of the most intelligent men on the planet, and he's been engaging with these ideas for his whole life. So it doesn't come easy, and so you should bear that in mind. That being said, in the spirit of what I said earlier, I think it's important to get a sense of what the takeaways should be, so that when you leave tonight, you have a certain sense of a framework from which you can further engage after you buy this book, and you delve in a little bit further. So the goals are fivefold. I would like everybody leaving the room tonight to have a sense of what's bothering Roger with respect to string theory, fashion. I would like them to have some sense of what's bothering Roger with respect to quantum mechanics and the foundations of quantum theory, the faith. I would like them to have some sense of what's concerning Roger in terms of the particular state of entropy at the Big Bang, which has led to many of his developments, most recently including his theory of conformal. What's the next word you want to use? Do you want to use cyclic or do you want to use crazy here?
No, cyclic is the correct.
Okay.
When I first thought of this idea, I realized it was going to be considered as crazy by everybody, so I got in there first and called it crazy.
Okay. So conformic cyclic cosmology. I would like people to, so that's issue number 3. Issue number 4, I would like you to have some understanding of what Roger means when he invokes fantasy in terms of inflationary cosmology and what bothers him about the theory of inflation, some rough way. And lastly, some idea as to why he's so excited about twistor theory. So again, no details, no great mathematical structure, but enough so that you can say, okay, I have a framework now. I have a certain sense of what's driving this individual and what's been driving this individual. And now I can engage in more details by picking up this book and getting into it. The format for this evening's conversation will be just this, an informal conversation, talking about those 5 different areas, and then at the end of which we'll have a Q&A with the audience. Again, I think we all have some experience with Q&As. I certainly have a lot. So the tolerance for somebody who wants to point out that there was an error on page 231 of the book will be extremely low. The tolerance
I'd like to know that, actually.
What's that?
I'd like to know these things. Yes.
Or to proclaim and purport their own particular theory or what have you. So we're looking for genuine engagement, a genuine question to ask Roger. Which brings me to introducing the gentleman to my left who needs no introduction, but I'm going to give him one anyway. So Roger did his undergraduate at University College London before moving to do his PhD at Cambridge University. And he followed that with a spate of fellowships at Bedford College, at St. John's College, Cambridge, at Princeton University, Syracuse University, King's College London, and University of Texas at Austin. This was, just as a side note, back in the days when reasonable people went to the United States of America to pursue thoughtful agendas. Those were good days. Upon returning to the United Kingdom, Roger took up a faculty post at Birkbeck College and then moved to Oxford as the Rousball Professor of Mathematics. And he is now the Emeritus Rousball Professor of Mathematics at Oxford University. His lists of achievement in the mathematical sciences and physics are quite frankly too numerous to mention, but they include, famously, his singularity theorems for black holes and work that was extended in collaboration with Stephen Hawking on cosmological scales. Cosmic censorship hypothesis, Weyl curvature hypothesis, Penrose tilings, twistor theory, Penrose diagram. Anyway, it goes on and on and on and on. Spin networks. He is a remarkably accomplished individual, and he was knighted in 1994 for his services for science. On top of that, he is, in addition to being one of the most spectacular intellects I've ever encountered, he's also one of the nicest people you'd ever want to meet, and that is indeed a very unique combination. Ladies and gentlemen, Sir Roger Penrose. So I thought we'd begin, as promised. Let me just put my watch here so we don't speak too much, with fashion.
Sure.
So I'd like to talk about string theory, or rather I'd like you to talk about string theory. And let me start off by asking you a couple of questions. One comment that certainly struck me that was in your book was in the early days of string theory, and as you know, of course it's gone through many different incarnations, but in the early days of string theory, you talked about the fact that you were very enthusiastic about the direction in which string theory was going, because there seemed to be a direct link to Riemann surfaces, Riemann 2 surfaces. So I'd like you to talk a little bit more about that, what that means, and why you were excited.
Well, I should explain that this has to do with certain areas of mathematics that I find particularly attractive. And one of the most important features in mathematics is the theory of complex numbers. So you get used to the idea of a real number. Well, you can measure something as a distance along a ruler or something. But if you go backwards as well, you can have negative numbers. You can take square roots of positive ones, but if you try to take a square root of a negative one, you have a bit of a problem. And so this system of real numbers gets extended by introducing a number which you might say is an invention, which is the number I, whose square is -1. So you say that one little bit of invention. And then you use that number and combine them with real numbers, and you get a system of numbers which I regard as completely magical. It has many features that you introduce I because that solves a particular equation. If you like, x squared plus 1 equals 0. Now, you can't solve that with a real number because that would always, x squared plus 1 would always be a positive number. It could never be 0. But if x is I, then that's a solution. And there's -I is also a solution. But just that one equation, and you solve all equations. So you take any algebraic equation whatsoever, any number of any coefficients, and they can have complex numbers as coefficients, you can always solve them. And it seems to me the first step, if you like, is an invention, but the rest of it is all there, given to you. Right. So there's sort of magic. And this happens again and again. There are many features just in the mathematics which to me seem completely magical. I think one of the things that struck me most is that if you have real functions, then they can be, I'd be a little technical, say, they can have different degrees of smoothness. You can differentiate them a certain number of times, and maybe you get stuck at a certain point. But with complex numbers, if you can do it once, you're never stuck. You can solve, you can use power series, you can differentiate as many times as you like. It's infinitely smooth automatically. That's another thing. And they're just one after the other, totally magical features, which seem to be this one little thing at the beginning, and you get all the rest of it free. And it seemed to me that wouldn't it be wonderful if these numbers lie in any sense at the basis of the way the physical world operates. And then I learned about quantum mechanics, and I found suddenly these numbers appear in the formalism of quantum mechanics, and they're there. It's not as though they're sort of artificially put in. The theory would not work if it weren't for these complex numbers. Right. You can go beyond it. There are things called Quaternions, which are generalizations of complex numbers, and they don't commute. AB is not the same as BA, and they're a very attractive system, but they don't have the magic. And people have tried to put Quaternions into a theory of complex numbers, and it doesn't work. There's something about the magic that you see in the mathematics which begins to reveal itself in an unexpected way in the initial discovery of quantum mechanics and quantum mechanical features, and how you describe the theory as fundamentally based on these complex numbers. So I had this feeling that maybe you could carry this further, and hiding somewhere in the nature of the world that at first sight looks as though you measure things, time is measured with real numbers, distances is with real numbers, that hiding behind that is this complex world which governs the way things operate.
So the fact that originally there was this link with these Riemann surfaces, which in turn
Yes.
linked to complex numbers, which in turn was the right way of expressing, or at least a potentially
right.
fundamental way of expressing
Perhaps I
quantum
should
theory.
explain a little bit more, because you see, the idea of there's things called Feynman diagrams, which is the way that people calculate using in quantum field theory, particle physics. And these, the diagrams look like straight lines joined together, and it's like a particle. You imagine the time is progressing, and the straight line represents the motion of a particle. And then it can split into two. This one can join onto another one, and so on. And you get these complicated combinations of particles coming together and going apart again. And each one of these diagrams, called a Feynman diagram, represents a very specific mathematical expression. And then you sort of fit these together, and you can get absolutely amazing calculations which give you extraordinary precision. Sometimes, I think Feynman used the example that you calculate the magnetic moment of an electron to a greater precision than the width of a human hair in relation to the distance from New York to Los Angeles. So it was that kind of precision, and it's better now. One has even more precision.
Right.
But in order to get that precision, you have to do a bit of cheating here and there. Now, the cheating is a bad word, because it's not really that. It's sort of seeing ways to evade infinities. Because you find that if you simply use these expressions in the Feynman diagrams, whenever it gets at all interesting, the answer technically is infinity. And that's useless. So what people do is they find, well, you can find certain classes of these diagrams, and you can factor them out in a way. Well, let's not go into details. But there are ways which you can get rid of the infinities by putting them all in parcels and throwing them out, if you like. And so you can use these tricks to get finite answers out of the Feynman diagrams. But it's admittedly, there's a bit of trickery. It seems to work extraordinarily well, but it would be nice if you didn't have to use that trickery. And the idea of the strings was, okay, instead of having a little particle, these lines representing the history of a particle, you have a little tube. There's a little loop. That's the string. And now it's a sort of pipe. And then these junctions where they join onto others of these lines, these pipes, it's a bit of plumbing, you see. They join together. And you have these complicated, and there's nothing infinite in it. It's all finite, and these things are interpreted as these Riemann surfaces. So these are a Riemann surface, I explain. You see, if you have a curve described with real numbers, well, a real number is like a line, you see. Whereas if you have the complex numbers, they fill out a plane. So a complex one, a space which is described by one number, if it's a complex number, it looks like a surface. And these things are called Riemann surfaces when they close up and form complicated topologies. They can be simplest one's a sphere. You can have a thing looking like a donut, an American donut, I should say, with a hole in it, or a thing with an American pretzel, which can have lots of holes in it. And these things, if these are described as these complex curves, if you like, which means surfaces in the real sense, they have amazing mathematical properties. It's going back to the magic of complex numbers again. Right. And these strings, the history of a string is a little tube, and then instead of having a sort of sharp place where they join onto the other ones, these tubes join on smoothly, and they form these beautiful Riemann surfaces. So when it was described to me that this was a new theory, I thought, wow, this brings in this idea of this complex analysis into a very fundamental, at a very fundamental level in physics. And rather than having these infinities coming out, we can work out things with perfectly finite calculations.
Of course, this was the early days of string theory.
Very early, yes.
And
in the 70s, I think. I can't remember exactly.
And it was invoked for rather different reasons than it's invoked today, and we don't have to go through all of that. What I would like to go through, although a quick aside, it seems to me that a German pretzel also has holes in it. It doesn't have to be an American pretzel, right?
Yes.
Is there a difference between a German pretzel and an American pretzel?
I'm not sure. You see, they're probably the same. I think pretzels maybe are universally the same. Do they have the same number of holes? 3 holes, is that it?
I'm not sure. Anyway,
yes. Never mind
about
that.
You became despondent, notwithstanding your initial excitement for the reasons that you just gave, when it became clear that string theory had, at the time, 26 dimensions.
But this was, yes.
And then it later, due to whatever, various different things, supersymmetry and so forth, it was reduced to 10, but that's still a whole lot of dimensions too many. And so the principal concern that you have with string theory, many people, of course, have all sorts of concerns about testability and experiment and all of that. That's a whole other ball of wax. But my understanding is the primary concern that you have with string theory has to do with these extra dimensions, in this case 6 extra spatial dimensions. And to understand what your concerns are, I think we have to talk a little bit about functional freedom.
Yeah.
And so I'd like you to, in answer to this question number 1, what's bothering Roger about string theory, and what is it about these extra dimensions? We have to start talking about functional freedom. So over to you.
Yes. Well, you see, when people ask me this, I think I described in the last section in the book that I had 2 reasons for not liking the extra dimensions. I had my public reason and my private reason. So we come to the private reason later, if you like. But the public reason, which I certainly
we're in
maintain,
public after all.
Yeah,
So.
it's in the public, yes, so why not? Was this functional freedom question. See, the thing is that people say, well, yeah, there are 10, whatever it is, 22 or 10 extra dimensions. See, originally it was 26 dimensions. They needed space and time altogether, so that's 22 extra ones. And then they got it down to 10 dimensions, so that's only 6 extra ones, which is supposed to be an improvement. Although they never gave up on the 26, it's still there, and this is a problem. I've always had it. Sometimes it's a bit of a confusion about which is the number of dimensions there. But the point that they kept saying, I mean, the official answer is, these extra dimensions are small. Now, what does that mean? It means that they're sort of wrapped up into a little loop. And the example often given, and I give it in the book too, is the example of a hose pipe. So you imagine there's this pipe lying on the ground, say, and you're a long way off, and you can just see it as a curve. So it looks like a one-dimensional thing. But you get close, and you see it's got a surface which is actually 2-dimensional. So forget about the interior of it, it's just a surface. So it's a 2-dimensional surface. But you don't notice that until you get really close in. So the argument is that the extra dimensions are tied up into a little loop or a little knot, a little shape, which you don't see because it's tiny. Right. And so that's the normal argument. Now, the problem I had is this thing called functional freedom, which you're raising here. And that is, roughly speaking, it's a thing that people don't, I think they used to talk about it more than they do now. It's you see, how much freedom there is. Suppose you ask in this room, how many possible electric fields are there? You see, there are obviously infinitely many of them in the theory, but that's a cop-out. You can be more precise than that. And you say, well, at each point, the magnetic field or electric field can have a certain strength, and it could point in a certain direction. And that's 3 numbers. 3 numbers per point. So you say the degrees of freedom in this would be 3. But it's in 3 dimensions also. So the functional freedom, you really have to look at the appendix to understand this better. Right. But it's like what I would say is infinity to the power 3 times infinity to the power 3. Now you have to make sense of all those infinities. And you can. And this was a thing that was basically argued for by a great French mathematician, Élie Cartan, who was solving equation in very, very general terms, and wrote a great book on this subject in the early years of the 20th century. And even before that, there were Italian geometers who were playing with these ideas. And the amount of freedom in these different systems you can describe in terms of what's the top index in infinity to something to the 3 it is in the top. And the 3 refers to the dimensions of space. Now, if you have a bigger number of dimensions of space, it doesn't matter how many components there are, the amount of freedom in this thing utterly swamps what it is in 3 dimensions. Right. So the number of electric fields, whatever kind of field you like, in in 4 space dimensions, or 5, or 22, whatever it is, will absolutely swamp anything we see in physics. Now, what happens to, well, why don't we see that all over the place in these theories? Well, that's a real problem. Now, the normal argument, although they don't talk about it this way normally, the normal argument is you can't excite these extra dimensions because in order to excite it by the lowest mode of excitement, you see, these are ideas that come from quantum mechanics. You can have a hydrogen atom, and you can excite it from its ground state to the next state, and that requires a certain amount of energy. And the amount of energy you would need to excite this lowest mode of these extra dimensions would be enormous. What do they mean by enormous? They mean something like the energy in a large, really sizable artillery shell. Now, it's what's called the Planck energy. It's actually a bit more than that would be needed, but never mind about this. No, I think it more or less doesn't make any difference. And what they say is that this is so big that you could never achieve this with an accelerator. You see, in particle accelerators, they're thinking of making a particle shooting at a huge speed. Well, it never gets faster than the speed of light, but it can get more and more and more and more energetic. So the amount of energy in that particle, it can be a certain amount. And this certain amount is far, far smaller than this artillery shell. And in order to make an accelerator, which would achieve the energy of that artillery shell, which is what you need in order to excite these extra dimensions, you would have to have an accelerator which is the size of the solar system or something, and way off out of the picture.
Right.
But then it struck me, this is ridiculous, because just to excite that one little degree of freedom in the extra dimensions, it's for the entire universe. So it's not as though you're taking an accelerator and trying to excite it here.
In that one particular place.
It's for the whole universe. Right. Now, for the whole universe, this artillery shell is utterly ridiculously small. And I talk about the Earth's orbit around the sun and how much energy there is in the Earth's orbit around the sun. Well, millions and millions and millions and millions times this artillery shell energy. So why is just a little bit of that energy going to disturb these extra dimensions? And there's no argument. I've never, you see, I brought up an argument like this in, I think it was...
this was for Hawking's 60th
2002.
birthday, right?
Yes, it was a conference in honor of Stephen Hawking, whatever his birthday was at that time. And I gave a talk. I was somewhere else first. I could only go at the end of the conference. And I gave the last talk in the meeting. And I said, well, look, I probably won't escape from this room without being tarred and feathered, you see, because I was questioning this whole idea of these extra dimensions, because there were world experts in string theory there. And... well, the next day, I didn't get tarred and feathered. The next day, in fact, I went in. This was a conference, a sort of popular conference at the end of the main conference. And I went in, and immediately Gabriele Veneziano, a very nice chap, is one of the founders of string theory, and he came up talking. He said, well, look, well, and he complained about something. He said, no, I don't mean it, it's this. He said, I see. And at this point, Michael Green came up, who was another great figure in string theory. And he came up and he started attacking me. And he said, no, what about this, you see? And then Gabriella said, no, he doesn't mean that. He means this. And then they started arguing with each other. So I snuck off.
And that's the end of the story.
And then I sat down at lunch afterwards. I was sitting down at this table. And Lenny Susskind came and sat down. Now, I should say Lenny Susskind is one of the great proponents of string theory. And he was, in fact, the one who first mentioned to me the early ideas of string theory, which I was very taken with. I thought they're really great ideas about these Riemann surfaces. That's before the dimensions went up, you see, when it was still three-dimensional space and one-dimensional time. And he sat down opposite me, and he said, you're completely right, of course, but totally misguided. And I tried to think, what did he mean by that? So I thought, the interpretation I made is, yeah, we know all that stuff, but you shouldn't distract us because
somehow it will be figured out.
That's right. We're disturbing with this great search for truth, you see, and little mathematical details, we'll figure that out later.
So my encapsulation, tell me if I'm off base, is that using these ideas of functional freedom that you should read in Appendix A2 and Appendix AA when
Yeah,
you buy
Appendix
this,
A.
when you buy this book.
Right. Yes. That's the easy part, easiest appendix.
Yeah. There, you will find that according to contemporary string theoretic views, that there are these extra, let's say, 6 dimensions that are supposed to be curled up in such a way that they don't interact with us in the normal course, but in fact, there's an argument that no, they should be excited, and that would lead to instability of the theory.
And also it's worse because the main problem is, you see, the obstruction for exciting these extra dimensions would be quantum mechanics. That's the argument, you see. Classically, I don't think there's any argument. It really wouldn't work. But you could say, because it's like a quantum mechanic, like the hydrogen atom thing, and these energies are discrete, then you have to excite that first energy level, and that's too difficult because it requires all this energy. But I say that argument just isn't right. And also, you can see it's not even quantum mechanical because you don't have to excite. I won't go into that, but that's in the book too. But then when you look at it classically, it's even worse than that, because once you do excite them, it collapses to a singularity. And this is ironically, this was a theorem that Stephen Hawking and I proved much before, and you can prove that it goes singular, almost certainly. And it's totally ignored. So apart from these responses I had on the next day after my talk there, nobody from the string theory body has ever come to me, written to me, emailed me, or anything to say, look, your argument's wrong for such and such a reason, or, yeah, that's a nice idea, or anything. Just zero. I've had no response of any kind whatsoever on these.
And this brings up a sociological point that hopefully we'll have time to get into at the end, which is, of course, why you call this fashion. Yes. There is a certain sense of inertia in aspects of this community where people might not be as willing as they perhaps should be to consider objections and other possibilities. But let's move on to faith.
Yes.
And the faith, as I understand it correctly, is faith in quantum mechanics, not just faith in quantum mechanics in everyday quantum experiments, but faith in the idea that we can extend the range of quantum mechanics indefinitely, basically.
Yes. I should explain it. It's completely different. You see, sometimes people say about string theory, quite legitimately, that there are no experiments to test it. That's not, it's certainly true, and I agree with that criticism, but that's not my criticism. My criticism is that it doesn't hang together as a proper theory of physics, no matter how beautiful the mathematical ideas are, and a lot of them are extremely attractive as bits of mathematics, but as a coherent physical theory, it doesn't hang together. Now, when it comes to quantum mechanics, it's completely different. There are vast arrays of different types of experiment confirming quantum mechanics one after the other. The theory is crazy, but it works extraordinarily well. Sure, it's also a lot of the mathematics is extremely beautiful. You have it's very beautiful mathematics. The experiments all work, but it's crazy. Now you see people argue, well, it's only crazy because we're not clever enough to understand it. It's a question of interpreting the theory correctly. If you have the right interpretation, then you will see it makes sense, but nobody really has the right interpretation. Well, lots of different interpretations people have.
You have this wonderful image / metaphor that I understand from your book came from the bicentenary of Hans Christian Andersen,
yes.
or something close to it, with
That's
the mermaid.
Right. Yeah.
This idea that there's the quantum world that goes about doing its own thing according to its own rules, that is called, represented by the letter U for unitary, but
right.
which perhaps we'll get to in a moment. Then there's the classical world that we all know and love. And the question is how you connect those two and this distinction between U, C, and R. R being the way that one can go, an active measurement, effectively.
Yes.
So perhaps you can talk a little bit more about what.
Yes, I said this was the Hans Christian Andersen Society asked me to give a talk in Odense, or however you pronounce it. And it was because it was coming up to the 200th anniversary of his birth. And I had written a book. I couldn't think why they'd asked me, but I had written a book which had the title The Emperor's New Mind, which was a play on the Emperor's new clothes. And so I presumed that was the reason they'd asked me. So I thought, well, I can't use that one again, but I'd like to think of another Hans Christian Andersen story, which was related to ideas I was worrying about at the time, which had to do with the foundations of quantum mechanics. So after lots of deliberation, I thought about the mermaid, which in various different respects, I only mentioned one of them, which is the one described here. It's actually on the back of the book too, but that's a slide I used for giving lectures, which is the one I actually gave in Denmark. Is a transparency. And the mermaid, you see, she has the bottom half of her as a fish, you see. So she lives partly in this strange undersea world where these strange creatures entangled with seaweed and all that sort of thing. So this represents the quantum world, this mysterious world there. And then the top half of the picture represents the classical world. And I use the letter U for the so-called unitary evolution, or the Schrodinger equation. That's the evolution according to the rules of quantum mechanics. And then the classical world, C stands for classical, and then R stands for the reduction of the state, or the collapse of the wave function. See, this is the way you use quantum mechanics. It's completely crazy, you see. You have this evolution according to Schrodinger, his equation. Schrodinger himself was pointed absolutely clear. Schrodinger was worried in just the same way as I was. He was worried, and this is why he produced this example of what's called Schrodinger's cat. He said, well, look, you could do an experiment in which, according to his own equation, Schrodinger's equation, the cat would have to be both live and dead at the same time. And that's ridiculous. Therefore, there must be something wrong with my equation, his equation, that is, the Schrodinger equation. That's more or less what he was saying, but it's not interpreted that way by people. People tend to say, oh, no, you have to believe the Schrodinger equation. The cat is dead and alive at the same time, but something, well, maybe it's because that's not the whole story. It's entangled with the rest of the universe, or maybe the cat is dead and alive at the same time, and somebody comes to look at it, and that person then becomes, in a sense, two conscious beings, one seeing the live cat and the other the dead cat, and there are these two parallel worlds which coexist, and somehow our consciousness threads its way through these multiplicities of worlds, which is where you're led. If you believe that if you have a hold to the faith is that the Schrodinger equation, or unitary evolution, is true at all levels. Then you are either forced into this multi-world, many-world interpretation, which is logical enough. That's where many of the philosophers in Oxford, that's the route they take. And I can see why they take that route, because they're too timid to say, you must be wrong. And when I say you, I mean you. the unitary evolution must be wrong at some level.
Yeah, you give an interesting point, and I want to get back to hopefully trying to maybe summarize things a little bit, but since we're on the many worlds interpretation,
yes.
You say it, if I understand you correctly, it could be possible, or why isn't it the case that a classical observer, wouldn't see a superposition of these particular things? We don't, of course, see a superposition of things, but we could see classical objects or whatever it is in a superposition. Let me get back, because I suspect that we may have gone perhaps a little bit too far, too fast. So let me back up if I may. Here's my sense of things, and so tell me where I'm wrong. My sense is we have these mechanics. We have a procedure to be able to make measurements on these small quantum mechanical systems, and that's described by this state vector that is evolving according to this unitary evolution. Yeah. And because of the inherent linearity of the system, this thing represents a system which can be in several different states, generally is in several different states simultaneously. Yep. So it's a little bit of this and a little bit of that and all the rest of that. And there's a very clear understanding of how this thing evolves in time. Yep. And lo and behold, you and I, or a detector, or some classical thing, makes a measurement, and that very act of measurement, what they call, collapses this wave function. So that instead of it being right before the measurement, it was in this linear superposition of these different states. We make a measurement, and it's in this particular state.
Yeah.
And so, to use your language, you have this U world of the mermaid, where it's in this linear superposition of different states. The mermaid, being a classical individual, recognizes that it's, after having made the measurement, after this R business, it's actually in one particular state. And so one question is, what is this wave function? Is it real? Does it represent any sense of reality? Is it a sense of what we know? And this is this whole question of quantum.
Well, that's part of it. You see, that's one of the loopholes that people go. They say, maybe, you see, there's this thing called the Copenhagen interpretation, which more or less Niels Bohr and Heisenberg came around to this view to say this is how we must understand quantum mechanics. It's a provisional view, certainly, because what it says is this piece of apparatus, you can't treat it. I mean, think of a Geiger counter. There's a particle emitted, and it enters the Geiger counter. Now, that particle is a quantum object, so that it could be here or it could be there all at once. The state, according to the quantum state, could share its existence in various different possibilities. Now, one of these possibilities is that it enters the Geiger counter. Now, the Geiger counter has to be treated as a classical device. So it clicks or it doesn't click. If it clicks, you say the particle went this way. If it doesn't click, the particle went some other way. But the machine itself is, after all, made up of particles itself.
Right.
It's made out of all the same quantum constituents of everything else. So it wouldn't just click. It would be click and not click at the same time. You see, but that's not the way we experience detectors. They either click or they don't click.
Right.
Or we hear a click or we don't hear a click. Is it the hearing of the click which is somehow making it actually click? And you get into all these philosophical discussions. And the question that you raise, okay, is the wave function, the thing you used to describe these different alternative possibilities for the particle, is that really a mathematical fiction? And it's not really there, in some sense. It's just a rule that we have. And that was basically the Copenhagen interpretation view. So there's no reality to that quantum state. It's just a piece of mathematics that we use to calculate things. And it's not real. But then it's very hard to maintain that view, because where does something become real? I mean, at what level is it real?
Right.
I mean, is it not real?
Right.
And it doesn't really hang together. So people have been arguing about these things endlessly. But they don't say, maybe quantum mechanics isn't completely right. That's the puzzle I find. You're presented with this puzzle. Is it a philosophical puzzle that you don't make sense of these ideas? Or is it just the physics isn't right? And to say the physics isn't right, well, you see, I tend to quote authority, which is not a good thing to do in science. But Einstein obviously thought there was something wrong. Schrodinger himself thought there was something. That's clear. That's why he introduced the cat. De Broglie, who introduced the idea of particles being waves, thought there's something wrong. And most surprisingly, in a sense, Dirac, who is the person more than anybody else, introduced the formalism that is universally used for quantum mechanics. And I have a nice quote in the book who says more or less, quantum mechanics, it works beautifully well. Nobody would question this formalism, but like any other theory, it's got its limits. It's a provisional theory. Someday it will be replaced by a better theory. Right. I think he's utterly right. I mean, the way Dirac says it is very Dirac. If you know things that Dirac says, you can see it's very, very Dirac. Very simple, simple-minded, right to the point.
So I have two things to say. I'm going to ask you about, very specifically about how we test things, because you've got a scheme for how you can actually test the limits of quantum theory that brings in gravity and so forth, and I'd like you to describe that. But before I do, I want to assure the audience that no cats were killed in the making of this book, because if you look at Schrodinger's cat experiment, they're actually cats that go into different rooms. So, so you can rest assured.
I have a humane cat experiment, yeah.
But if you can talk a little bit about picking up on what you said before, which is nobody looks at the limits of quantum mechanics and when quantum mechanics can be wrong, but you are looking at the limits of quantum mechanics.
No, to say nobody does is
okay,
not quite fair. There is a small group.
Right. So so you are, and how are you, the YOU, broadly attempting to do that?
Well, you see that to say there's something wrong somewhere, there may be people who would agree with that, but they would say, what's wrong? Well, it might be here, it might be here, it might be here. But in my view, what's wrong has to be to do with gravity. That there, and I gave an example. Let me not describe any example there. I'll just tell you the, roughly speaking, a particular experiment which has been developed for, I don't know, 20 years, maybe up to this point, by a very good Dutch experimenter, Dirk Bouwmeester, who he and a number of colleagues have for quite a long time been trying to develop an experiment which is something of the following nature. See, the idea is that if you consider what happens when you bring gravity into the experiment, you realize that there is a conflict between the rules of quantum mechanics and the principles of general relativity. And the principle of general relativity that I concentrate on mainly is what's called the principle of equivalence. And that says that a gravitational field locally is the same as the effect of an acceleration. So if you're in a lift and the lift is going up, you feel a little heavier. That's just the same as having a slightly stronger gravitational field. And this is the main point that Einstein used to produce his theory. I mean, it was a point that was understood by Galileo, it was understood by Newton, but they didn't make it into a theory. The point about Einstein, he said, look, this is a key point telling us a new route to go to understand how to do gravitational theory. And this resulted in general relativity, which is now has these wonderful confirmations in the LIGO observations with black hole encounters a long time ago in the early universe. But anyway, gravitation theory has this principle of equivalence. And you can see, if you look into the details, that quantum mechanics is not quite consistent with it. And it leads one, with a bit of hand-waving at certain places, but a fairly logical argument, to the conclusion that a superposition, let's say you could have this glass here, and you could put it into a superposition of being here and here. So you can make... Well, then it's two glasses, so you have to be careful. I'm talking about one glass.
No, so but I'm just in different places. So
imagine that this is not two glasses, but one glass in the superposition of two places. That's right. And the idea is that that superposition will become one or the other, actually, physically. It decays into the state which is one or the other in a time scale that you can actually calculate. It involves the amount of gravitational interaction. If you tried to pull this glass away from that one, say if it was two glasses, how much would the gravitational force be pulling it from here to here? And you use that measure of mass displacement, and that gives you a lifetime. It's a sort of reciprocal of that. The more mass is displaced, the shorter will be the lifetime. So for a glass like that, it would a ridiculously tiny fraction of a second. It would go less than I can snap my fingers, of course. It will be one or the other. However, if it's much smaller, if it was a neutron, it would be probably the age of the universe. Something like that. And there are experiments, very good experiments, to show neutrons are in two places at once. You know, tracks that it makes, it's got to be considered to be both here and there at the same time. And you get used to that after a while. But what's the difference between this glass and the neutron? It's not that they're made of different things or not, it's that this glass is a lot heavier. It's a lot more massive, I should say. And so that this measure of mass displacement is much huger, and therefore the lifetime is much smaller. For the neutron, you'd never see the decay into one or the other. But for that glass, you would. Now, is there a point at which that could be detected experimentally? Now, this experiment, which Dirk Baumeister and his colleagues, and I think there are some other experiments also, different places in the world which people are doing, but this is the one I know particularly. It involves putting a little mirror, and that mirror is pretty tiny. It's about 1/10 of the thickness of a human hair, just too small to see, but it's, what is it? You take a photon, and this photon is split into 2 beams. So it's a superposition of being there and there. The one that goes this way hits this little mirror. Well, it's not enough impact to hit it with 1 photon, but what you do is you reflect it backwards and forwards against another mirror, and it does that about 1,000,000 times. And that 1,000,000 times is about enough to push the mirror away by the pressure of that photon on it, so that it's displaced by roughly the diameter of an atomic nucleus. Not much. But that amount, and it's on a sort of spring, and you bring it back again after a while, and you see whether, when it was in a superposition of 2 locations, it became one or the other, spontaneously. Is it big enough to do that in, say, second, minute, something like this, depending on the details? And that's the kind of thing that this experiment is geared to look for.
And so the idea is that it's the effect of gravity that is
It's the gravity
reducing.
of itself. We should make the point here. It's not the Earth's gravity you're looking at.
Right.
That cancels out
Right.
from this calculation. But it's the gravity of it on itself, which is pretty damn small,
Right.
as you might imagine. But it's enough on this calculation for it to become one or the other.
So it's the effect of its self-gravity. It's the effect
Yeah.
of Einstein's gravitational field that is forcing this otherwise permanently stable quantum state to actually collapse.
That's right.
And this is this objective reduction, this OR
That's right.
that
That's
you
the
allude
idea.
to. Now, we don't have time to talk about this, and this is actually not in the book. This is in The Emperor's New Mind, which you should also buy. But you speculate that, in fact, this feature, this objective reduction of the state vector, is actually somehow linked to consciousness as well.
Well, that's not in the book, you're right.
Yeah.
I tried to keep away from that. Well, this is an idea which I've been developing with Stuart Hameroff. Let me very quickly say, I have a picture in the book where you see it's as though that if the thing's in one place or another, the universe has to make a decision. It's because the space-time of that tiny little mirror, if it's in one place or in the other place, they're slightly different. The 2 gravitational fields are slightly different. And space-time doesn't like to be in a superposition of 2 places at once. That's the sort of argument. So it decides on one or the other. Now, that decision that it makes to one or the other is what Stuart and I refer to as a moment of proto-consciousness. See, the idea is that the universe has to make a choice. Now, it's totally unimportant as far as the universe is concerned which choice it makes, so it's effectively random. But if you have this choice somehow at a much bigger scale and tied up with all sorts of other processes which are meaningful in one way or another, then that is the kind of choice that one actually makes with a conscious decision. So it's not that this is conscious. I'm not even saying that. That's why we say proto-conscious. It's the sort of brick out of which the building of consciousness is constructed. So the idea is that consciousness needs a lot more to be meaningful in some sense, whereas the actual individual choice, which the universe has to make, is now a much more controlled choice, and which is the idea of what consciousness has to do with. Now, that's not in the book.
Right, I've taken us a
Deliberately
little bit further
Yes.
afield.
Yes.
But you believe that there is, so tell me if this is right or if this is wrong. My understanding is that at some level you think the principles of general relativity, the principle of equivalence, which led to general relativity, is a more fundamental thing than, say, Schrodinger's equation, or are principles upon which the quantum world is based, insofar as one can see you're looking at me quizzically, so maybe this is completely wrong.
Okay. Well, I wouldn't quite use
there's
it,
a bit of a
yeah.
tussle, it seems, going
Yes,
on
yes.
between
Yes.
general
Let me
relativity
put
and
it
quantum
another
theory.
way. You see, there are a lot of people, when I say a lot, it's a fairly small proportion, but there are quite a few people who are actually working on this area of what's called quantum gravity. Now, what they are trying to do is to combine these two great theories together. And the usual view, the term quantum gravity more or less says this, because if you say quantum something, it means use the rules of quantum mechanics and apply it to the something. In this case, what it means is use the rules of quantum mechanics and apply them to gravity. So we will have a quantized theory of gravity. And what the people who work on this area, it's the sort of thing that I would have thought of too. Let's leave that aside for the moment. But this area is what's called quantum gravity. Now, what I'm trying to say is, yes, we've got to combine quantum mechanics and general relativity at some level, but one shouldn't try to impose the rules of quantum mechanics on those of gravity. It must be a more even-handed marriage between the two, that there is give on both sides. And so there has to be give on the quantum mechanical side as well. And I'm not trying to say that the principle of equivalence is more fundamental than the laws of quantum mechanics. I'm not sure I would say that at all. But I am saying that there's good evidence that it's a good principle. And that general relativity is now tested to an extraordinary precision too. It's not just quantum mechanics. And there are effects, well, as we now know from these LIGO observations, very good evidence that black holes are really there. We've had good evidence for that before. But black holes seem to be there, and they come about from taking this theory very seriously. They're not there if you take a more older Newtonian view of what gravity is, the fact that space-time gets distorted, and so on. So the principle of equivalence is sort of lying at the basis of that whole approach to gravity. And I do say it's a very fundamental principle. Whether I'd say it's more fundamental than those of quantum mechanics, I'm not sure at all.
But you can certainly use it to probe quantum
Yes.
theory in this
Yes.
particular.
I'm saying that it should not be violated in this particular experiment.
Yeah.
I may be wrong. See, that's the point of the experiment. Maybe it will show that this idea is wrong.
Before we move on to entropy in the early universe, I just want to make an aside because you mentioned some of the diagrams. So another remarkable feature in this
Yes.
book is that all the diagrams, right, were done by you.
All of them except for the computer graphs, which are a few of them.
Okay.
And the one or two, the Escher picture I did not draw.
Right, of course. but anyway, a remarkable number of diagrams were written by Roger, which, just before we move to entropy, brings me up to a very small anecdote. So years ago, I was able to corral Roger into serving on an advisory board of this thing that I was involved with, which is a terrible, thankless task, and no serious person who has better things to do.
Well, you more or less
wants to do it.
invented the institute, the Perimeter Institute.
What's-
You more or less invented it. the
Well,
Perimeter
yeah, but I'm
Institute.
talking about the thankless task, not my thankless task. I'm talking about your thankless task that you had to do. So we'd hold these meetings, which were not terribly interesting meetings, and they'd be filled with all these top scientists. And the very first time I met Roger, I saw him, and he was, it wasn't the very first time, but one of the earlier times I'd met him, he was around the table, and there'd be 8 or 10 or whatever it is of these very famous and highly regarded scientists, physicists, and I'd watch him taking notes frantically the whole day. And I thought, what is he doing? This is not his thing. Why is he? I was just completely mesmerized by this. And I went up afterwards and I looked, and he was doodling the whole time. And the cartoons and the doodles that you drew were actually remarkable. So you're an extremely accomplished artist, and so the diagrams are worth the book in and of themselves. But let's move on to entropy. So there's a problem with entropy at the Big Bang.
Indeed.
And there are two aspects of this. One is the problem itself, which I'd like you to explain. But the other is the fact that not as many people as might be optimal seem to be paying a great deal of attention to it. So first of all, what's the problem? And maybe one way to start, obviously you can start whatever way you want, but you have this, again, this very interesting diagram of two different types of entropy, of a gas in a box and then stars collapsing or what have you, in terms of defining what entropy is and where the problem might lie.
Yes, well, it's the sort of thing I now call the mammoth in the room. It's, what is the second law of thermodynamics? What does that say? It says, more or less, things get more and more random as time goes on. The measure of randomness that's being used here is a thing called entropy. And so, roughly speaking, the entropy of a system is how random it is. You can tighten that up, but never mind, that's what it's saying. And the second law of thermodynamics tells us that entropy is increasing all the time. Okay, that's an observed fact. I mean, it's an impressive, all the time you see evidence. You're just showing it right there when you pour that. The water comes out and so on and so forth, the way it does it. Anyway, now that means, just say the same, I'll say the same thing in a slightly different way. To say the entropy increases with increasing time is the same thing as saying entropy decreases when you go back in time. So I'm just saying the same thing. So it goes down and down and down as you go back and back into the past. But if you go back and back, way back into the past, where do you get? Well, you get to the Big Bang. Now, the Big Bang, what's the best evidence for the Big Bang? Well, they have this cosmic microwave background, this radiation, electromagnetic radiation, light, like a microwave light, coming in from all directions, and it has a certain spectrum. That is to say, you look at the different frequencies and you look at what the intensity is for different frequencies. And this shape of the curve you get is an extraordinarily close fit to the Planck Curve. Now, what's the Planck Curve? Well, that is what you get with what's called thermal equilibrium. In other words, what does thermal equilibrium mean? It means maximum entropy, a state of maximum entropy. So what you're looking at, according to the shape of this curve, is that the Big Bang, at least when the microwave background was produced, was in a state of essentially maximum entropy. You go back and back and back in time, the entropy is going down, down, and down, and reaches a maximum. Now that's, you see, that's the mammoth in the room. You see, isn't there something funny going on there? You see, people don't seem to worry about it. I'm always puzzled by that, particularly because this microwave background was actually a prediction of standard theory. Gamow and Dickey predicted in the Big Bang model you would get this spectrum and all that stuff. So they're not surprised. Yeah, sure.
Right.
So what's the puzzle? And what's the answer? And people sometimes say, well, the answer is the universe was small in those days. There wasn't much room for much entropy. That's wrong. So let's not follow that one. The mathematical cosmologist Tolman, who was a contemporary of Einstein, completely understood it. So that's not the answer. What is the answer? Well, the answer is that the entropy was, in fact, very low, but only in one feature, that is gravity. That the universe was extremely uniform in those days, and that is an observed feature. And as time developed, it started to clump. You made stars. The stars got hot. The hot star is in contrast with the dark background. That's a very low entropy situation. We live off it. The sun's a bright spot in the dark sky. All life on Earth, well, apart from the tubes in the bottom of the ocean, but that's from some radioactive stuff. But basically, life on Earth comes about because the sun is a bright spot in a dark sky. And that imbalance is what plants use. If the whole sky was the same temperature as the sun, it would be completely useless. It's because of that imbalance between the dark sky and the bright sun. That's a low entropy state. And it came about because the sun, okay, there are all sorts of things, thermonuclear reactions and so on. But the main point is the sun's there at all. And it's there because of gravity. It condensed from this uniform distribution of gas, dust, whatever it was, and produced a star. And there you see tapping off from this low entropy state. See, you say two kinds of entropy. I have this picture with a gas in a box. If you have it tucked up in one corner to begin with, it spreads out. into the box. That's increasing entropy, getting more random. But if you have a galactic scale box with stars in it, they may start out uniformly, and then they'll start to condense into certain regions, and then ultimately black holes. And this process of clumping represents an increase of entropy. It goes the other way around. That is to say, they're both going in the direction of increasing entropy. That's fine. That's the second law. But in the case of gravity, it causes more clumpiness. In the case of almost everything else, it goes more uniform.
Right.
So the uniform nature of the early universe was the way in which it was low entropy.
So the mystery, if I understand it, is we have this radiation, the CMB from the early universe, that follows this black body spectrum perfectly, or almost perfectly, to all intents and purposes perfectly, which represents a state in thermal equilibrium, which is the highest amount of entropy. So how is it possible that at the early universe, which has to have the lowest amount of entropy, because of course it's becoming an older universe eventually, and then entropy is going to increase according to the second law, how can it start off in the maximum amount of entropy? And the answer is, well, it's got a lot of entropy, its maximum in terms of the CMB, but it has no entropy in terms of gravity. That's right. Because everything is nice and smooth, and there's no clumpiness involved. Things haven't clumped together at all. So the question is, how did that happen?
Exactly. That's right. And you see, people often would say, well, you've got to understand, if you're going to understand the Big Bang, get deeper into what's going on, you need quantum gravity. So that's a conventional view, and I used to hold that view myself. But the trouble with that is, why does quantum gravity somehow give you this very uniform initial state? Whereas if you think of a collapsing universe with black holes and they're clumping, and it's an unbelievable mess at the end. And this unbelievable mess, turn it round, why wasn't that what we started with?
Right.
And the uniform state that we seem to have had in the very early universe, you can even work out how unlikely that was to have happened by chance. And this is where these numbers that I talk about sometimes, 10 to the power, 124. And this is an absurd,
very unlikely,
utterly absurd improbability.
Right.
So why was the universe this very, very uniform initial state?
Right.
If it was quantum gravity, why didn't quantum gravity come in at the end with these collapsing things with the black holes? But evidently it doesn't. It doesn't stop black holes coming about. Right. It doesn't work that way around. It's asymmetrical in time. You've got to have something. Second law is fundamentally asymmetrical in time. You've got to have something asymmetrical in time which sets it off.
So the question is, why is gravity turned off, if you will, or why is it that things are so smoothly distributed? Your matter is so smoothly distributed, and there are different people who have different types of solutions for that question,
well, you see,
or at least
why,
sort of solutions.
See, the thing is to start with the what, not with the why. You see, how do you describe that very uniform state, geometrically or mathematically?
Right.
And I had a way which I call the Weyl curvature hypothesis. Don't worry about that, because I'm not going to explain that. It's just that was my way, not saying why it should be like that, saying what was it like. It was like that this thing called Weyl curvature was zero in the initial state by
decree.
By decree, more or less, yes. So it was a hypothesis. But then my colleague, Paul Todd, in Oxford, he was a student of mine a long time ago, but he does wonderful things now. And one of the things he did was another way of stating this idea. You don't say that the Weyl curvature was something. What you say is, now here I have to explain conformal. Let's backtrack a little bit and talk about space-time. The space-time is this four-dimensional structure, and it has what's called a metric. So that means you can have a notion of distances. It's better to talk about times. That works out to be a much more precise measure of scale. So you say there is this notion of time, how clocks measure times, different clocks going along different histories will have slightly different measures of time, but that time is a function of that world line, the history of that clock's path. Now, that's conventional general relativity. But this notion of the metric that this the thing called metric, which is determined by the way the clock, how fast the clocks tick, if you like, is defined by 10 numbers at each point. There's a thing that you write GAB or G mu nu or G, whatever it is. And in the subject, you have a G with a couple of little indices. And those define the 10 numbers at any point, which tell you what the metric structure is there. Now, most of that information is telling you how light behaves. That tells you the speed of light. So you have a thing called the light cone, which tells you the history of a flash of light. And you have to imagine at every point in space-time, there's one of these little cones. And that little cone is telling you, it's telling you the history of a flash of light. As time progresses, think of it upwards, the flash of light gets bigger, and the space-time track of that flash is a cone. So you have these cones conceptually all over the space-time. Now, if you just know the cones and not the scale, so you don't have any clocks yet, you just have the cones, that's what's called conformal geometry. Now, conformal geometry is, I like to illustrate it by that nice Escher picture they've got.
Right.
There are two versions, one in chapter 1 and one in chapter 3. And that shows you a kind of geometry. It's called hyperbolic geometry. Don't worry about that. It's a kind of geometry in which there are angels and devils or fish, and they are represented. And you look at as they get towards the edge, there's a circular boundary to this picture, and that circular boundary represents the infinity that these creatures in the picture, that's their infinity. But they're squashed down. In order to get it all on the picture, you have to squash it down so that they appear to us to be getting smaller and smaller.
But the angles are preserved as they go.
The point is that angles are preserved, that's right. The angle on the fish's wing or the fin or something, or the devil's wing or something, that angle is the same no matter how close they are to the edge. Small shapes are correctly represented no matter how close to the edge. But the scale is not. The scale can be squashed down. That's a conformal representation.
Right.
Now in space-time, what does conformal mean? It means just the light cones. You don't know what the rates of clocks are. Now, rates of clocks, we have extraordinarily precise clocks now. You can measure I think from about here to here, about a centimeter or perhaps less. The slowing down of a clock that's lower down from slightly further up because of gravity can actually be measured. I mean, clocks are so precise that you can even measure the so-called gravitational redshift at that level, which is extraordinary. Now, why are clocks so precise? Well, because they depend on the two most fundamental equations of 20th century physics. One of them has to be Einstein's E equals mc squared. The other is E equals h nu. The nu is a frequency. That's Max Planck's. Energy and frequency are equivalent. Einstein says energy and mass are equivalent. Put the two together, mass and frequency are equivalent. So that means if you have a particle, a stable particle of a definite mass, it is a little clock. It is itself a little clock with an extraordinarily precisely defined frequency. Now you can sort of magnify that up to something we can actually measure. That's what these incredible devices do. But the point is that mass and clocks, if you like, are equivalent. Now, that's fine. If you've got mass around, then we have to have the geometry that Einstein needs for his theory. That is the metric geometry of space-time, which is not only the light cones, but also the scale. But if you didn't have any mass, you would just have the light cones. Now, this was a thought I had when I was worrying about the universe, which I do from time to time, especially times like now, but never mind about that. I was worrying about the very, very late universe, if we ever get there, the very late universe, which I call it the boring stage, is when there's nothing left but black holes sitting around. That's pretty boring. But what's very boring is when the black holes start to evaporate away by Stephen Hawking's process of black hole evaporation. This will, for the biggest black holes around, the supermassive ones that seem to be around, these black holes will evaporate. They will gradually disappear. For the biggest ones, it will take about a googol years. What's a googol? Well, it's 1, 0, 0, 0, 0, 100 zeros, years, roughly speaking. After a googol years, that's what I call the very boring era. It's really boring. If you want to know what boring is, that's boring. And it seemed to me this was a pretty unhappy future for our wonderful universe. Now, this is admittedly over an emotional argument, but it did seem to me an uncomfortable kind of future. That's what modern physics is telling us. We're going to end up with this extremely boring thing forever and forever and forever. But then I began to think, well, who's around to be bored by this universe? Pretty well photons. And it's extremely hard to bore a photon. Well, it probably doesn't actually experience anything, that's one reason. But the more important reason is that it doesn't register the passage of time. It zips along the light cone. It doesn't hit any of these surfaces which measure the ticks of the clocks. It doesn't experience time at all. From where it's created to infinity is nothing. The photon, it created and boom, there it's at infinity, right, as far as it's concerned. So I thought, well, maybe from the point of view of massless things, it's not so boring. And in work I'd done a long time ago, I had used these conformal squashings, like the Escher picture, where you squash infinity down to a finite place. And you can do calculations on the boundary. It's great fun. You can work out energy carried by gravitational waves and all sorts of things like that. So I played around with these things before, but this was a different way of playing around with it. Think of that Escher picture. Think of outside. Is there an outside to this picture? Okay, the world of these creatures is within that circle. Outside, that's cheating. That's not part of their world. But still, there's an outside in the picture. So you could imagine something going along which respected only the conformal structure, the photon, and it goes right through to the other side. What's on the other side? Well, nothing as far as we know. But the photons should seem to continue their existence. And then I couple this with the idea that Paul Todd had about how to characterize those models of the universe in which the Big Bang is free of gravitational degrees of freedom. And his argument is that these are those which, when stretched, now it's the other thing. You see, the picture I was doing about infinity was squashing infinity down to a finite region. Now this is stretching out the Big Bang to a finite region. If you can do that stretching out smoothly, regularly, that is Paul Todd's condition. He doesn't say there's anything before this stretch. Right. But again, you can say, well, particles, as they were closer and closer to the Big Bang, the energy was so big that their masses become completely irrelevant. They're basically massless things, just like the photons at the end. And so they don't care about the metric either. So they would think they should have come from somewhere. Where did they come from? Well, the idea I had was that is the infinity of a previous eon. So I'm using the word eon, A-E-O-N, to describe our Big Bang to our infinity, exponential expansion that we seem to see out there. Squash all that down to make a nice, smooth future boundary. That works. Right. That is one eon. There was, I say, a previous eon, very much like ours, which had its Big Bang, its ultimate remote expansion. And it has this exponential remote expansion, which is interesting, because although you didn't mention this yet, in the fantasy, there was this issue of what's called inflation, which is very much part of current cosmology.
Right. We're just about to get there. So let me just interrupt you for a bit to see if this makes sense.
Yeah, go ahead.
So there is this mystery regarding the second law,
yeah,
and why the universe, the early universe, had the shape that it did.
Yeah, yeah.
There were various approaches that you had with the Weyl curvature hypothesis and so forth to be able to hypothesize some through some sort of conformal invariant, some sort of understanding of this. That, through Paul Todd and other people, morphed into this notion of a more general conformal map, if you will, or conformal picture that led to a full-blown CCC that we don't have time to go into here. But it was motivated by this early universe entropy concern at some level, which I want to leave people with, which is why is the universe, the early universe, in this peculiar state of low entropy? How can that possibly be be understood and addressed. And you have a fully fledged, very interesting theory that with all sorts of observational possible predictions and all of that we don't have time to go into. But that's a key question, and my understanding is a source of frustration for you is that many people aren't even worried by the question so much as accept your particular response to the question. And this brings us, without further ado, right into fantasy, the last one, which is inflation. So we're going to connect things in a weird way, but I want to pass it over to you to set it up with, which is, what is this cosmic inflation business anyway? Why was it invented, or at least why were some versions of it invented? What problems was it trying, or what problems were it? Was it?
Yes.
What problems was it trying to solve?
Yes. Well, there's one that it was initially trying to solve, which we can ignore. That was the magnetic monopoles. Let's not think about that. But the main reason people argued for it was, I should say, that the inflation is supposed to have taken place in, the first 10 to the minus 32 seconds. That means 1 over, this is 1 with 32 zeros, the reciprocal of that number, of a second. Pretty ridiculously tiny fraction of a second. And in that tiny fraction of a second, the universe was supposed to have undergone an inflation, an exponential expansion. This is the expansion that we do seem to see now, which is referred to as the result of dark energy. I call this Einstein's cosmological constant because that's exactly what you expect from Einstein's extra term he introduced into his equations. But that's what we see in our current universe, is it is expanding in this exponential way. So its state of expansion is, the rate is proportional to the state, if you like. So it's expanding at a rate which is increasing as time goes on. And the argument is that there was a stage like that, but in a very, very tiny initial phase of the universe, 10 to the minus 32 seconds. Now, this was supposed, one of the main reasons, not the monopoles, I forget that, one of the main reasons was that it smoothed out the universe, so the argument went. That you imagine the irregularities were there, but the stretching, this inflationary phase, smoothed them all out. Now, from a very early stage, I just didn't think that's right. And you can see from quite general arguments that it can't be right. The general arguments have to do with looking at a collapsing universe and all the equations.
Well, it's time reversible, so you can just switch it on its head.
And you can see it doesn't get rid of them. The type of mess that you should start off with in general is such a mess that it's not removed by stretching. It's like a fractal. You stretch it out, it looks worse. The more you stretch it, the worse it looks. It just doesn't help. But it had been presented as one of the main reasons for the smoothness of the universe. But it can't be the reason, because that smoothness is the low entropy that we see. And low entropy is the very specialness. If the inflation did it, it's got to have already been lower entropy before the inflation. Right. I mean, these are sort of very mammoth-in-the-room arguments, which for some reason, very little attention was paid to. Now, I have to be fair to inflation. This is, in my argument, a bad reason for inflation. It was one of the reasons that it was strongly put forward still as being a good reason for inflation. I think, when I first heard of inflation, I thought, well, that won't last a week. How wrong I was. But the reasoning was still correct. That is to say, it doesn't get rid of the irregularities. But it turns out there are other reasons, basically 2 or perhaps 3. One of them is a thing called the scale invariance of the fluctuations. That's a technical point, so let's not worry about it. Another one, which is to do with correlations, which you see in this temperatures of this, the temperature variations in this microwave background are related to each other over
the horizon problem.
Yes, outside this, what would have been the horizon. So there must have been, now this I accept, either there was an inflationary phase or there was a pre-Big Bang phase. There was something before the Big Bang. And the before the Big Bang scheme will do that. It probably will also do this scale invariance thing, but that requires more understanding. Basically, the roughly speaking idea is that in a certain sense, there was an inflation, but it wasn't in the first 10 to the minus 32 seconds. It was actually before the Big Bang.
Okay, but contemporary inflation, as I understand it, a key issue is why is the universe so smooth and homogeneous? Right?
Well, that's
and the question is, the question is, an inflationary period in the first tiny few microseconds of the universe to blow everything up doesn't explain that.
It doesn't work
because. Because
it only works if it's already smooth.
Right, it already works. So you're begging the question, basically.
Yes.
So this is the fantastical argument, which is fantastical in the sense that it's hard to understand why people would still subscribe to it under those circumstances. And so the response is what, in your view? Some people invoke the anthropic principle. Some people say something else. What is the response of somebody? If I'm a diehard inflationary theory person and I hear you say this, what would I say to you?
They probably go to what's called internal inflation, which is, I should say, even more fantastical. It's that inflation has a probability of happening anywhere at any moment, and that somehow. If you get a state of the universe which is smooth enough, then it does it. I don't want to go into that.
Best not to.
It's even crazier than. But I should say, you see, when I wrote this book, I introduced this title. I was worrying about inflation and certain other models, which I didn't believe in. As the time went on, 13 years since I initially gave these talks in Princeton. I produced my own crazy scheme, which I've just been describing to conformal cyclic cosmology. And I thought, well, my scheme also is fantastical, in a sense. But we really need fantastical ideas, because the universe is fantastical. I mean, even quantum mechanics, you have strange things. You need a fantastical theory to explain the odd things that we see. It's just got to be the right fantasy. So I take a little bit of a softer line with regard to fantasy and say, okay, fantasy in itself isn't such a bad thing. You actually need it. It's just got to be the right fantasy.
So let me move a little bit before we're almost ready to open it up for questions. Before I do, and I'm going to forsake the twister stuff because I think that's going to be too difficult to...
well, I've more or less, in a sense, you've said it, because it's this argument that these complex numbers should play a deep role.
Right. So let me, instead of explicitly asking about twisters, let me try to, and I'm going to ask about a few sociological things before we open it up. But let me get back to something that you alluded to earlier, which is that you said some time ago that you had a public argument against string theory in terms of the dimensions and functional freedom and so forth, which is illustrated here. But you also had a private argument, which is alluded to at the very end of end of your book.
So I want you want me to give that one?
I want you to give that
one. Well, it's public now. It's in the book. It was really, you see, this idea of twistor theory, which, as you say, I'm not going to go into in detail. It was trying to take note of certain rather remarkable features of A, relativity theory, B, quantum mechanics, which have to do with these complex numbers. So it's not just that the complex numbers form a basic part of quantum mechanics. They also do, if you look at it in the right way, a basic part in relativity theory, which has to do with the celestial sphere and the transformations on that sphere when you move very fast, and relativity does to it. And these, again, look like complex numbers are the way to treat it. So the complex numbers were the link between relativity and quantum mechanics. When you look at the picture, the relativity picture in this way, now which has to do with the celestial sphere. Now the idea is the celestial sphere in this picture has to be looked at as a Riemann sphere. This is going back to our original discussion. So it's really a one-dimensional, one complex dimensional surface, and the transformations are exactly what you would get from that. So the argument is that the complex numbers are showing themselves also in the structure of space-time, if we look at it the right way. And the twistor theory is meant to be a way of looking at physics which brings out this role of the complex numbers. Now, the private reason, you ask me, is this simply only works for 3 space and 1 time dimension. Now, I always regarded that as a real plus. I said, well, we've got to understand why, in some deep sense, space has 3 dimensions and time 1 dimension. Well, this idea only works when it's like that. So this was a big motivation for twistor theory right from the start. So if somebody comes along and said, well, I've got a wonderful idea, and really there are all these extra space dimensions, I say, oh dear. I want only 3 dimensions, because twistors and things like that only work properly. You can find versions of twistors in other dimensions, but they only work properly with all the nice features which come out of it in 3 space and 1 time dimension. So that's the private reason. Yeah. Public now.
So there are all sorts of curious things that physicists seem to be subscribing to. They're prey to fashion. They don't seem to be motivated, at least some of them, to address some of these key fundamental questions head on. They seem to be begging some questions at some level. Are these examples of fashion, faith, and fantasy that are happening in contemporary theoretical physics, is this worse than it used to be, do you think? And if so, why do you think that might be?
It's probably not worse, but it might be. I mean, I give examples of earlier ideas, of fantastical or fashionable ideas going back in history, so it's not so new. I do think there probably are reasons why it takes hold now. And I shouldn't say this, but I partly blame the internet, because it's now so easy to get information, and you could just pick it up without any kind of critical judgment. Well, you get lots of critical judgments, but these are just people sending in their ideas, you see, which often don't make too much sense. But nevertheless, people are allowed to say, well, anything they like. But it's not really I don't know. You see, I think there is a factor here which is present in current. The way that information is too easy to spread, in a way, and that ideas, you're caught in this mass of different things, and you have nowhere to go. So you tend to look at what are other people doing, you see. Right. And so that tends to focus on the fashionable ideas.
What about other sociological factors? Money, funding for research?
Yes, that's certainly true.
In some areas, the lack of experiment. I mean, the lack of experiment, I think, is relevant in some ways. In some ways, it's not. In terms of mathematical inconsistency, it's not terribly relevant. I mean, some of the things you're pointing out are internally inconsistent, arguably mathematically. Yeah. But certainly, there are issues of funding. There are issues of different groups that are perhaps lobbying or arguing more strongly than they were before. Is that worse than it used to be in terms of our tolerance for welcoming people pursuing more iconoclastic paths?
It might be worse. I'm not sure. I would have to, you need to be more of a historian of science than I am to see. But it certainly is true. Well, first of all, in experimental physics, experiments have got so expensive. You see, it used to be people could set up something in their room, you see, or people well off enough maybe in their castle or something. But it wasn't so hard. People could design experiments that you could see the results of without huge expense and without enormous numbers of people working on it. But now you think of the CERN experiment, you think of the LIGO, you think of these are huge things with enormous amount of preparation over years and years and years, lots and lots of money involved. And who decides which experiments should be set up? Well, there are committees, you see, obviously, of scientists, distinguished scientists. And these scientists are likely to be people who are distinguished because they've had important ideas in the progress of science previously. And so, therefore, their main interests are in those areas which have already been fashionable for some, or they've made it fashionable, maybe. I mean, I'm not quite sure what the moral is here, because clearly those are the people who should be judging. You want people who have the expertise to make these judgments. But there is presumably a tendency for people to design or think about funding experiments. You have to have a lot of top-notch theorists and experimenters who are deciding what directions are for new experiments. So it probably does tend to freeze things in currently fashionable directions. To some degree, I wouldn't say it's... But the other thing I think you were worried about were graduate students and so on, wanting to know what area to work in. And I've had problems with this. I mean, we had quite a big group working on twistor theory, which was fine. There were a lot of problems in the area. But you tend to find after they left, they'd gone into banking or something else. You see, they wouldn't continue with doing twistors. Oh, a few of them would do.
A lot of string theorists go into banking, too.
Yes, they go into banking as well. That's probably true, yes. I mean, that's where the money is, so you can see why they do that. But it's hard to get jobs often in these areas. Twistor theory had a bit of an advantage in a certain sense. The physicists paid no attention to it, but the mathematicians did, because there were certain spin-offs, if you like, in areas of mathematics, which attracted a fair amount of attention.
Very good. I think it's time to open things up for questions. So if I can just, so there was one person.
Howard, just so you know, hi. What we're going to do is, because there's only 2 microphones, we're going to take a couple of questions from downstairs first of all, and then we'll go upstairs and do upstairs.
Okay.
So for the moment, just downstairs, people, please put your hands
there's
up.
a gentleman right next. I'm not even sure it's a gentleman. There's a person right next to you with his or her hand.
That one? Or this one?
The one right in front of you.
One in front of me, there you go.
Hi.
No, it's not
You've mentioned philosophers a couple of times, but if you are a philosopher currently, there does seem to be quite a lot of, I don't know quite what the word is, but often you seem to be a bit looked down on, perhaps, by some of the scientific community. If you are of the opinion that philosophers can bring something of worth to the physical sciences,
yes,
do you have any advice for current philosophers on how to do that and be heard?
Yes, I think that's a good question. I mean, I do have a lot of respect. When I talk about the Oxford philosophers, I have an awful lot of respect for them, because I think, as far as I'm aware, they know more physics than any other philosophy department that I know of. They really do know their stuff, but they do tend to be attracted, being logical people, into the many worlds view. And in a certain sense, I would say they're not quite doing their job, you see, because one of the troubles with quantum theory is it doesn't have a sensible ontology, a consistent ontology. Well, that's a problem. You see, the philosophers should say, well, look, your theory doesn't have a sensible ontology. Go and improve on that, you see. But I think they're a little bit too timid, and they say, well, you know, they must know what they're doing, and so we shouldn't tell them what to do. Of course, they shouldn't tell us what to do, but I do have a lot of respect for the philosophers, and I think it's important in analyzing the way things went in the past, and certainly, I like to talk to the philosophers at Oxford a lot, and I think I get a lot from them. So I think I'm not quite sure. The question was what should they?
Do you have any advice also for philosophers?
Well, I'm talking now about philosophers of science, of course, and philosophers of physics in particular. My advice there would, can they think a bit more seriously that there might actually be something wrong with quantum mechanics, rather than trying to make it actually make sense.
You don't suggest that they go into banking as well?
Oh, absolutely not. Well, if they want to make money, I think they should go into banking. Yes.
There's a gentleman right up here in the front row, and then the person in the back as well. Just could you wait until the microphone, because other people can't hear.
In the ideal world, I'd love to come down to Oxford and chat with you and Peter Hacker about consciousness.
Yeah.
But being as that's probably not possible, I'd like to ask you, how do you combine the micro with the macro in regard to consciousness?
Well, you see, the idea that the uncertainty or the probabilities of quantum mechanics, or the fact that you don't have a deterministic world in the quantum world, is quite an old one, and that people certainly thought that might have something to do with conscious decisions and so on. But the argument tended to be, well, an electron might decide whether it goes this way or that way. But that is not my point of view. You see, the electron is at some level where it makes both decisions at once. So as long as it's still down in the quantum world, below the sea level, according to my mermaid picture, as long as you're still down in the quantum level, all these things do happen at once, and the decisions are not made. The decisions only occur when there is sufficient displacement of mass, which has to be coherently done in a way which doesn't lose information. And so at first, when I wrote my book, The Emperor's New Mind, I was very troubled. And I thought, well, I don't know how this can work. Maybe when I've learned enough about how the brain works, at the end of the book, I will have an idea about this. I got to the end of the book and I didn't. So I trotted out something which I don't believe at the end. But the advantage there was that Stuart Hameroff, who had been an anesthesiologist in Arizona, and he had his own ideas about consciousness, and he thought that microtubules, it's not at the level of neurons, but it must be at a lower level where you might expect some kind of quantum coherence to be preserved. And he said, perhaps you don't know about these things, which he was right, I didn't. So I learned about microtubules, and the view we formulated was that there is something at that level which could influence the strengths of neurons. So it's that neurons, in a certain sense, provide the control. If I move my hand like this, it's the neurons acting in a certain way. But what is it at the deeper level which controls the strength of connections between neurons? And that could be at a level where microtubules and other parts of the cytoskeleton and molecules which have great symmetry and so on could be collectively acting in a way which would reach this level where the amount of mass displacement is sufficient for the choice to be made. So I think this rough answer to your question is that. I hope that helps you to some degree.
Great, thank you. Sorry, I think we should move on because there are lots of people with their hands up.
Yes.
Gentleman at the back.
Yes. Could you tell me who or what determined the value of the universal constants? And I thought why can't we predict them theoretically?
Yes, well, there's this great puzzle about constants of nature. There's a bit of discussion about this in the book. Some people argue what's called the Anthropic Argument, and they say that if these numbers... Let me explain, some other people may know what's meant here. One of the examples is there's a thing called the fine structure constant, which is very important in determining the strength of electromagnetism. And this is a number which is roughly the reciprocal of 137. And Eddington tried to make a theory out of it being actually the reciprocal of 137. It isn't. It's observed not to be quite that now. But there are other numbers. Some of them are huge. The most obvious one is if you think of a hydrogen atom. It's got a proton and a neutron. It's got a proton and an electron, and they attract each other electrically, and they also attract each other gravitationally. Now, they're both inverse square forces, so however far apart they are, the ratio is the same. What is that ratio? Well, the gravitational attraction is weaker than the electric attraction by a factor of about 10 to the power 40. And you see numbers like this coming in all sorts of places in the constants of nature. And this is the thing which puzzles physicists. It puzzled Dirac, and he tried to argue that these numbers might be changing. It's an interesting idea, which turned out not to be correct. But it's a big puzzle. We don't know the answer. Maybe the Anthropic Argument, which says, roughly speaking, if these constants had different values, you wouldn't have life, you wouldn't have intelligent life, and therefore universes with those wrong, in a sense, values for these numbers, we couldn't be in that universe, but we could be in one where the numbers are right. So this is the sort of argument that people use. They say that these universes are all there stacked up next to each other in a sense, but we can only exist in one where these numbers have the right values. I'm very troubled by that argument. I don't like it. There is a discussion of the anthropic principle in the book, so if you want my point of view, I think the best way is to turn to that part of the book. But it's not resolved. There are one or two examples where the anthropic argument plays a role, in a genuine role. It usually plays a role which is more or less a giving up role, such as in string theory now, where according to conventional string theory, there, I forget how many it is, 10 to the 500 or something or other, different possible theories, and the argument is made that the only ones that could exist are the ones which people could live in. People have been taken in a very general sense. So
You're not the only one who doesn't like the anthropic principle. As you
Yes.
know, there was a famous American newspaper. Well, he was a mathematician, but he also wrote a regular column in Scientific American by the name of Martin Gardner. And he reviewed famously a book on the anthropic principle that had all these different types of anthropic principles with all these different acronyms. There was FAP and MAP and the strong and the weak
Yes,
and all the
yes.
rest of that. And he came up with his own anthropic principle in his review. I think it was called the completely ridiculous anthropic principle, or words to that effect,
Yes.
which of course
The
was crap.
acronym.
But that's,
Yes.
that was,
Yes, that's Martin Gardner.
he was a little bit more
Yes.
forthright, I suppose. There was a
Absolutely.
gentleman, one gentleman right here had his hand up, and then I think we're going to go upstairs.
How significant would you say your ability to visualize impossible scenarios was in your scientific career? How much do you think that was an important factor? I'm thinking of Escher and
Yes.
the impossible staircase, which you helped devise.
Well, I've certainly been somebody who thinks very visually. This is, when I think about mathematical arguments, I tend to think very visually. It's just what comes naturally to me. But the impossible, in the book again, there is a picture of this impossible triangle, which was stimulated by Escher. I went to an exhibition of his when I was a second-year graduate student, and then I produced this triangle, and then my father developed it into a staircase, and then we sent this to Escher, and he made 2 of his prints based on these. So we stimulated each other. But the impossible triangle, later on, I realized it was a curious thing. I was being interviewed for some article, I think what it was, and I was talking about twistor theory, and I was saying you can use twistor theory to solve Maxwell's equations, the theory of electricity, magnetism, and light. So this wonderful theory of Maxwell's. And you can formulate solutions of Maxwell's equations in this very neat twistor form. But to explain it properly, you have to do something called cohomology. And they said, this wasn't part of the interview, we were just talking. And so she said, well, what's cohomology? So I said, oh, there's no way I could possibly explain that at this level, you see. Then I went home, and I was sleeping, not sleeping, awake in bed, I think. And I realized that this impossible triangle is an example of cohomology. It's a very good representation of cohomology. So I went back and said, look, yeah, you can explain that. But she didn't use it. But in the book, again, I do use this example of showing it's something where you have an idea which is locally consistent, but with an ambiguity. So if you have a picture just on a flat piece of paper or a piece of canvas or something, and you draw something, now you don't know how far away that object is. It might be very far away and bigger, or it might be much closer and smaller, which would be the same shape. So there is that ambiguity. Now, as you go around, you might make use of that ambiguity. So when you've got round to the beginning, it's inconsistent. You have no consistent way of attaching a distance from you for that shape. And that's what cohomology does. It's an example which illustrates cohomology. So I thought that as a way of understanding this idea, which plays an important role, it's a sort of non-local feature of twistor theory, which in some respects reflects the non-local features that you have in quantum mechanics. It's one of the most mysterious things about quantum mechanics, is that you can't fully describe what's going on in any local region. You've got these non-local relationships between things in different places, which it's hard to see these effects, but you can do experiments which see them. And this is an example of a sort of cohomology idea. So it seems to me, although this is not developed very far, that these pictures do enable us to think about, in a more concrete way, some of these rather sophisticated mathematical ideas.
Great. The person with the microphone is, there's a gentleman and a lady right beside her that had their hands up. Yes.
I'm a little bit vague as to what you meant to say about Eddington and the fine structure constant. Were you dismissive of what he said, or?
Oh, no.
Because I'll tell you why I ask.
I'm not trying to be dismissive. I'm just saying that we don't know. It's a big question mark. And it may be, I mean, these are two routes that are possible, if you like. I think maybe there are others, but in my mind. One is that the numbers could have other values, and our universe just simply happens to have these values. And maybe it's an anthropic type argument that means we can only live in such a universe, and that's why the one we live in has these numbers. That's the anthropic argument. On the other hand, it may be, and I much prefer the other argument, maybe there is deep down some mathematical reason for these numbers. So these numbers, which are even the scale of 10 to the 40 or 10 to the 20 or whatever they are, maybe there is a theory which absolutely requires that number to have that value. And that the nature of the universe, nature of any universe which could call itself a universe, so to speak, has to have this particular value for these numbers. Now, we don't know. I don't know, certainly. I've never seen any good argument. You can present half arguments, you see, why. You see, there was this coincidence that Dirac was very puzzled by, that if you measure the age of the universe in sort of proton units or electron units, you come to a number which is like 10 to the 40, which is a bit like the ratio of the electric to gravitational attraction of a proton to the electron in the hydrogen atom. Now, is this a fluke? Or if there's some good reason for it, well, the age of the universe is not a constant. The universe is getting older. So that number won't always have that value. So in the future, that number will be different. So Dirac argued that all these numbers, which based on powers of 10 to the 20 or something, all changed with time, because the time was one of these units. But later on, it turned out to be wrong. Later on, there was an argument presented by Dickey and by Brandon Carter, originally by Bob Dickey, where he showed that the age of a main sequence star, like the sun, an ordinary star, let's say, the age of such a star depends on these proton to electron force ratio. And so the age of a main sequence star would have to be, in these units, something like 10 to the 40. And so therefore, if we happen to be the sort of being that arose on a planet going around a main sequence star, and most stars are like that, I guess, then that coincidence will be something we see, and that explains it. So that thing that puzzled Dirac actually has a sort of anthropic argument. I'm not sure if it's anthropic, but it's related to the ideas of anthropic arguments. Namely, that a star, an ordinary kind of star, has a lifetime, which means that beings which depend upon that star for their existence will see the age of the Earth in these proton units or something. It's something like 10 to the 40.
I think we have time.
I just want to say why I asked you that question.
No, excuse me. Sorry, we have time for two more questions, and there's a gentleman right up there in the middle. Thank you very much.
Hi, Professor Penrose. You've mentioned in your book and film, actually, The Emperor's New Mind, limits of artificial intelligence. For instance, you gave the example of tiling and geometrical structures where a computer tiles a certain pattern and then a human mind patterns the same pattern, and where you show the computer has a limitations where certain geometrical patterns are given and the human mind doesn't. So could you maybe elaborate now on what conclusions you draw about the possibilities of attaining artificial intelligence now, in the future, any future from such limitations?
I'm not sure I know the experiments you're talking about, but never mind. My argument basically has been that understanding, whatever it is, human understanding, is something which computers don't have. Now, they play very good chess if programmed appropriately, and as we know from recent in a recent example, they can play extremely good Go, which is a much bigger challenge than chess. And basically, they do it by brute force. I mean, you work out all the possibilities. Well, not all the possibilities, but a sufficient number of them that they can, the computer can make a decision on the basis of endless trying out of possibilities, and they can simply do that. However, there is this thing called the Turing Test, which is basically you're in conversation with a computer, and you have to decide whether the thing you're in conversation with is a computer or a human being. And although occasionally they may clock up the odd sort of success, in a sense, the conclusion seems to be that they're pretty hopeless at that. So even now, you see, Turing suggested this idea as a way of telling whether a computer can think or not. It's an interesting idea. And at the time he put it forward, he suggested maybe, well, when we have a computer which is 100 times better than the Manchester machine, it will achieve human capabilities. Well, I mean, that's far below. I mean, what people can do now with their machines is ridiculously more than that. But yet, they still don't seem to have a quality which could be argued to be an understanding. And that's what I claim is something which is not of a computational character. And I tend to rely on the Girdle Argument. This is a mathematical argument which tells you that in order to prove mathematical theorems, there's always a limitation if you don't have an understanding of what you're doing. That's basically the argument. And you can see very precisely where the understanding comes in. You've got to know what you're doing at some scale, whatever that means. And the knowing what you're doing is something which is not a computational activity. It's something which is what consciousness is in effect being used for. It's why it's evolved in animals, because there is a sense in which they understand what's going on. Now, what that means in any precise way, I don't know how to formulate that. That's the position I take, is that there is something going on in our conscious understanding of things which is not a process of computation and which you cannot simulate by computation, even though you can maybe get good approximations to it. Up to a point, you can fool people. But there comes a point where you see, no, it doesn't really understand anything.
So I think I'm going to call a halt to the questions here. I should say that Fashion, Faith, and Fantasy in the New Physics of the Universe will be sold around the corner, and Roger will be signing some books. So if anybody wants to go up to him and ask him questions after having purchased the book and signed it themselves, they should not hesitate to do so. I should also say, pushing my own thing, that there is a detailed series of videos of Roger on Ideas Roadshow, as well as detailed videos with Nobel laureates Tony Leggett and David Pulitzer, physicist Paul Steinhardt, Nima Arkani Hamid, and many more. So check out ideasroadshow.com. And before you go, I would like everybody to once again thank Roger for his presence this evening.
Thank you.
I would also like to thank Jim Walsh and Sid Rodriguez and all the people at Conway Hall for the work that they've done. Thank you all very much for coming. Have a pleasant evening and good night.